I'd like to go through the answers to the last lab that you turned in, the acids, bases, and buffers lab. A number of you missed some of these reactions, so I thought just to make sure you understand it fully, I'd go through these answers fairly quickly. Let's see here. I did an experiment in part one where I was exhaling into tap water, distilled water, and a solution I made by adding some drops of concentrated ammonia, NH4OH, into water. And you can see that the pH drops when I start exhaling, and that's because I'm creating CO2, or I exhale CO2 into the water, which makes carbonic acid. So again, most of you got all these right, but there were, some of the questions I think were difficult, and I just wanted to make you think about these a little bit. And you did a good job overall, but let me just clarify some of these in case some of you are wondering what the right answer was or what I was expecting to see. The initial pH of these solutions was all less than 7, and that's, in the videos I kind of misspoke or didn't realize that CO2 is in water if it sits out for a while. So all water, no matter if it's distilled water, is going to eventually get a slightly acidic pH when it's been sitting out for a while in a room. So that's why CO2 creates an acidic solution. It mixes with water to make carbonic acid, and that can dissociate to give a proton plus a bicarbonate ion. That can also dissociate again to give another proton and a carbonate ion. Let's see, I had the base at about 50 seconds here. So right about here I added it. That's about 50 to 60 seconds when the pH increases rapidly to distilled water. And to explain the change in pH when I do that, when you add ammonia, you can call it NH3 or NH4OH. Both are okay. Ammonia reacts with water. It's a weak base, and it pulls a proton off water. You get ammonium ion and hydroxide ion. That's why the pH jumps up, because all of a sudden you have excess hydroxide in the pure water. So you have a large jump in pH. If you just show the dissociation of this into ammonium ion and OH, that's fine too. It says in the above graph, I've pointed to the time when I start exhaling. Again, I already commented on this. Why does the pH drop when I do this? It's because CO2 mixing with water makes carbonic acid. So again, you get a drop in pH when you get CO2, carbonated water essentially. Number 5, I asked you, as you can see in the green graph, well, this is a black and white, but in this graph here, the pH drops only to about pH 8 after I exhaled into it for a while. Why is that? It's simply because I didn't neutralize all the OH. There was a lot of hydroxide in the solution, and I could have neutralized it all the way down to pH 7 if I had kept exhaling, but I didn't. I stopped. There was excess hydroxide present. And then part 2, I created a titration curve, and so this is just adding a drop of KOH to water, and you can see it. Water is not a buffer, so it just the hydroxide ions are not neutralized by anything, so the pH rises rapidly. However, when you take vinegar and slowly add KOH, the pH is going to slowly rise until it reaches the equivalence point. This is called the buffer region. It's because in this region you're creating a mixture of acetic acid molecules and its conjugate base, acetate ions. The pH at the beginning was calibrated to be at 4.00. That's the solution, the buffer solution I used to calibrate the pH probe. The pH paper I used turns blue in base. That was the answer to number 7. The answer to number 8, what color change in red or blue litmus paper would tell me that KOH is strongly basic? You're looking for a red to blue. The change I'm looking for is red to blue. If you put blue litmus paper in base, nothing happens. It just stays blue. One observation from the video tells you that tap water is not a buffer. Again, these rapid rise in pH when you add just 1 or 2 drops of KOH tells you it has no ability to resist changes in pH, so it is not a buffer solution. Question number 10. What's the initial pH of the vinegar at the beginning of the titration? It's around 2.62. Write the acetic acid dissociation that explains this low pH. Again, that's just the dissociation at this point before you've added base. All that's happening is some of the molecules of acetic acid are dissociating into protons and acetate ions. so you have a pH that's less than 7. What's the reaction that occurs when you start adding in base from this point up to this point? That is KOH reacts with 1 mole of that plus 1 mole of acetic acid gives you 1 mole of potassium acetate and 1 mole of water. This is the same reaction that we collected data on when we did the acid-base titration lab. Question 12b, why or how does this reaction produce a buffer? This was a little bit of a challenging question, maybe. Before the equivalence point, you have the limiting reactant is KOH. So you have excess acetic acid molecules, and every time you add a KOH, you convert one of the acetic acid into its conjugate base, the salt of acetic acid. So as you go further and further into the titration, the number of molecules of conjugate base is increasing, the number of molecules of acetic acid is decreasing. Eventually they get to a point where they're equal, and that's probably somewhere in here. And then eventually you come out of the buffer region because you add so much KOH that you use up all the acetic acid, and then at this point all you have is a solution of potassium acetate and water. So up until that equivalence point, the KOH, the base, strong base, is the limiting reactant. Question 13, at the equivalence point, all of the acetic acid has been neutralized. Write the reaction that explains why the pH is above 7. So if you look carefully, at the equivalence point, which is right here, it's about somewhere between a pH of 8 and 9. Why is it on the basic side? It's because at that point, all you have is potassium acetate. I haven't written in the potassium ions. They don't do anything. They're spectator ions. So the acetate ion is a weak base. It does pull off a proton off of some water molecules to create the original acetic acid and hydroxide. That's why the pH is above 7. You have a slight excess of OH ions versus protons, so the pH will be around 8 to 9. What's the main cause of the pH rise after the equivalence point? So from here upward, you still have this reaction going on. However, the amount of hydroxide that you get from that reaction is very small relative to the amount of hydroxide that you're throwing into the solution just by adding in excess KOH. KOH completely dissolves, dissociates into K plus and OH minus. So that's the main cause of the rise in pH after that point, is the excess base, strong base. What's the approximate pH at the equivalence point? Like I said, I accepted anything from 8 to 9.5 or so, because it's hard. It's not. I haven't shown you exactly where it is. It's somewhere in here. What's the approximate pH at the end of the buffer region? Again, the buffer region's right around here. So the end of the buffer region is somewhere in here. Just an educated guess. So that's somewhere between pH 5 to 6.5 or so. I accepted that as being okay. What's the approximate ratio between acetic acid and the acetate ion in the buffer region? 1 to 1 is the ideal ratio. Again, it is only really 1 to 1, exactly right there, halfway between starting and equivalence point. That's the point at which the moles of acetic acid equals moles of conjugate base. But it's roughly 1 to 1 in that whole region. Dissolving, the part 3, then I just gave you, I showed a bunch of measurements of pH of different household products and chemicals and things like that. And I dissolved ammonium chloride in water. It produced a pH that was less than 7. It was, I think, somewhere between 4 and 5. I don't remember. The reason why this is an acidic salt is because when it dissolves, it breaks apart into ammonium ions and chloride ions. Chloride ions are the conjugate base of HCl. They have no acid-base properties because they're such a weak base. But ammonium ion is the conjugate acid of a weak base, so it's relatively strong acid. It donates a proton to the solution, so you will have a slightly acidic pH when that dissolves. Number 19, why is the pH of this solution, sodium carbonate, basic? Same sort of reasoning. The salt completely dissolves to give you 2 sodiums, which don't do anything. They have no acid-base properties. But carbonate ions, being the conjugate base of a weak acid, have enough of a base strength to pull a proton off water to create bicarbonate and hydroxide, so you get a pH above 7. And some of you wrote a different reaction where this lost another proton to create another OH, and you combined them all into one reaction. That was clever of you as well. That's actually the summary of what's going on here. I've just written one step. Number 20, why is the pH of the solution of baking soda basic? Same reasoning. Baking soda dissolves, it breaks up into its ions. Bicarbonate ion is basic. It pulls a proton off water to create hydroxide. So again, the pH is above 7. What's the pH of vinegar? Again, it's a pure vinegar solution is right here, a pH of around 2.62. pH of orange juice is around 4.36, not quite as acidic. I asked you, what is the acid in orange juice that makes it acidic? Again, citric acid is the main acid that makes things like lemons and oranges and grapefruits acidic. But there's also, some of you put ascorbic acid, which is fine too. That's vitamin C. That's this molecule here. The number of acidic protons on a citric acid molecule is 3. All the hydrogens attached to the carboxylic acid functional group are acidic. So it has 3 acidic hydrogens. Ascorbic acid, only these 2 are acidic. So one of them is very weakly acidic. So I accepted 1 or 2 as the number of acidic protons for ascorbic acid. You could find all this info on Wikipedia and using the internet, which I'm hoping a lot of you did to get these answers. What's the pH of Coca-Cola? 2.62. That's just coincidence. It's the same as vinegar. The 2 main acids in soda that are, or in Coke, I should have said Coke, that are, explain why it's so acidic, are phosphoric acid, H3PO4, and carbonic acid, which is H2CO3. Some of you said citric acid, which I accepted because in Diet Coke, they actually do use citric acid. And I think citric acid is even found in Pepsi, which makes it taste slightly different than Coke, which I believe just has these 2 in it. These are weak acids. Why is an aqueous solution of sodium chloride neutral? It's because sodium ions and chloride ions are too weak to pull a proton or hydroxide off a water molecule. Sodium chloride is made when you take NaOH and HCl, a strong base and strong acid, and they neutralize each other. You get sodium chloride and water. You get a neutral solution. So you can only get an acidic or basic solution when you have a salt created from a weak acid or a weak base. As you see in the video, soap's a basic substance. What are the 2 main ingredients? Base and fat. Most common soaps are made with sodium hydroxide and beef fat. But you can make all sorts of soaps. You can use KOH, you can use other metals to create shampoos and things like that. But if you use liquid fat, you can get liquid soap. So it depends on the saturation level of the fat that will determine the quality of the soap, whether it's a liquid or solid at room temperature. I measured a pH of bleach to be very basic, 12.68, and the reaction that explains that is the hypochlorite ion pulling a proton off water to create what's called hypochlorous acid and hydroxide ion. So that'll do it. I will have your grades done by Wednesday, as I said, and I hope you all have a good summer.